So, welcome back everybody. Glad you made it. I was getting a bit scared yesterday when I was looking over campus and it was really empty. Well, it was off by a week or something. Slowly. How happy are you? You're somewhat relaxed. Not too stressed out with the other courses. With your assignments, with your lectures. Don't fall asleep straight away, not that relaxed. Goody. In that case, we have to talk about asynchronism. What do you remember about asynchronism? What can you still do in terms of asynchronism? To do some asynchronous programming, what can you actually practically do? Communicate without blocking somebody, is that necessarily asynchronous? Is blocking asynchronous or synchronous? It's synchronous. So that's not asynchronous.
Yes, that's what I'm saying, doing stuff without.
Other than, but not everything which is not blocking is automatically asynchronous. Can you do anything asynchronous in real life? Have you ever programmed anything asynchronous? What?
Like you can do like registering a callback or something rather than
registering a callback. In what language can you do that?
Java.
Sounds very good. You can also do it in JavaScript, right? Or async in JavaScript.
I thought you said programming language, sorry.
It has nothing to do with asynchronous. It's just a misnomer, just the wrong keyword. Okay, so we need more tools to actually do asynchronous operations. Why do we need asynchronism in the first place? Anybody give me motivation? Yes, unless you manage to synchronize the rest of the world with you, you will have occasionally the need to handle some asynchronous stuff in the outside world. If I don't want to do asynchronous handling, what's my alternative? So, before we go into this chapter, is there still a way around it? There's still a way to avoid that. What would you do to communicate with the rest of the world if the rest of the world is not synchronized with you? Just assume that for a second. Set up a buffer and then throw whatever they have into that buffer. Isn't that buffer asynchronous?
That's just a memory board.
There must be some mechanism by which they put something in the buffer.
Yeah.
Unless you're facilitating
polling. Yeah, sure. As opposed to doing it asynchronously, you can also try to look every once in a while. Right? If you look frequent enough, you possibly don't miss the other input from that side. So that's a possibility. Yeah. Currently, so yes, you need more pollers, more CPUs which are actually doing this active polling, because at some point you're running out of eyes to look at everything at the same time. You should do this over multiple CPU cores, and then you can do this concurrently, polling and looking at it. Yeah. Okay. Sure. Now, any downside? Obviously, if you do it all by polling, you have your CPUs busy all the time. That costs a lot of energy. And it may not be quite as precise, because if I have to poll as many different sources one by one, then I have time jitter in the process. If I can do it a bit more direct than that. So let's talk about actual asynchronism then. And we start with interrupts. You will use interrupts on your boards, obviously, and you will also, I think today, still see the syntactical construction, if you haven't found them in the code framework already anyway, how to set up interrupts in higher level programming languages. It's actually a lot easier than you think. But you still need to have understood the underlying principles, because without having understood the principles, you will run into a brick wall. If you do that, you will do it all wrong. The fact that something looks syntactically easy doesn't mean it is. Similar to the select and abort statements, which we will be using. Looks easy, doesn't necessarily need to be easy. So what do we need? We need interrupt control, context switching, and interrupt identification. Right. Interrupt control means you need to have the ability to program your external devices in terms of you are allowed to raise this specific interrupt under those specific conditions. Otherwise, I'm masking them away from you. Right? So enabling, prioritizing, how to create responses on your CPU. What happens if an interrupt arrives at your CPU? We'll talk about this in more detail. And then you want to find out where it exactly came from. It's not always a dead giveaway for a number of reasons, because the number of identifiable different interrupt lines on some CPUs is limited. You can only have so and so many interrupt priorities, and if you get an interrupt on a certain priority, and you still have 200 devices which you need to serve, you still need to ask a second time. So this was an interrupt on priority 5. That could still have been this, and that reason. You have to still poll and recheck what's actually going on there. What is really important is to understand which of these functionalities do require hardware support and which are software, in the software domain. Some do necessarily require hardware support. Are you clear about which parts of interrupt processing are hardware support and need to be hardware support?
So, CPU level, you're halfway through executing instruction or something.
Yeah.
It's the signal. So
Yeah.
there's not much software can do that.
Yes. So what do you expect the hardware to do?
At the very least, finish off the instruction of some of the process.
Yeah. Okay, let's talk about this in some more detail. Okay, first have a look at interrupt control. Interrupt control at the individual device level. I just come back to one of the devices which you already saw. We programmed this little National Semiconductor AD converter, and one of the register groups which we have not looked into is the programming of the interrupt setup for this whole thing. So let's look into this one, interrupt enable, interrupt status register. And here are all the possible sources which can trigger an interrupt on this specific AD converter device. It's quite representative. So this is classical for all of your little devices. Now imagine for every little chip device you use to contact and communicate with the outside world, you have a whole bunch of possibilities what can trigger an interrupt. For example, that the watchdog limit condition has been triggered. You still remember what the watchdog limit condition was in that specific setup? It was if I program the AD converter in the sense that I'm not interested in the value. I'm never reading the actual analog voltage converter into digital. I was only interested in, is this value exceeding a minimum or maximum value? So I program limits, and if these limits are broken, then I want to have an interrupt. I'm not communicating with my AD converter ever about the actual value on the input side. I just expect my AD converter to give me an interrupt if something specific happens. Or if a specific instruction has been triggered, if the conversion has been performed, why would you use an interrupt for that? An interrupt when the conversion has been completed? Why would you need that? Yes, but if I communicate with my AD converter, I say, okay, now please convert the value from my input line, from my analog line, into digital and give me the value. Why do I need interrupt that? things a lot slower than your CPU. So every time you do anything on the AD converter, particularly converting a value, this can take a lot longer than your patience will run for on your CPU. So you can run through hundreds of CPU cycles before this has been converted. So you do something else. At the end of the conversion, you want to have interrupt. Obviously for auto-searing and full calibration, because the calibration process is a lot longer than an actual conversion. If the sequence arrives at a pause, and if this is also classic, which you have on your devices plenty, if the device has been broken up, why does this require an interrupt? Same reason, because the waking up process itself, warming the whole thing up, getting the clocks in gear, getting everything synchronized, takes a reasonable amount of time. This doesn't happen instantaneously. So you can save a lot of power by powering your devices down and get them back up. But you also have to be aware, the moment you are activating the device, you have to be very careful. If you do this on your controller, you should be using your silent as well. Activating the device is nice. So how do you activate the device on the microcontroller? You remember what you actually practically do. You may still remember this from 2300. Yeah. Usually you have some form of enabler bit someplace, but that's the obvious thing. The other thing is that you have to provide power and you have to provide a clock. Providing power and a clock to your little device, which is a tiny area on the die, takes a bit for everything to synchronize and fall into place. So if you use this device in two subsequent machine instructions from your main CPU, you're almost certainly out of luck. Switching on my AD converter, give me the next machine instruction some information about the registers of this thing or anything else to communicate with this thing. You usually have 2 or 3 knobs after that just to give it a bit of pause and give it some reading before it can get to the end. Unfortunately, many hardware manufacturers are a little wishy-washy on the amount of time that it takes for some of the devices to come on. So it's easy to overlook that. They usually program this in their hardware abstraction layer. So the piece of software that you get to interface with the classical C interface, but they not always describe it in the hardware manual precise enough that you can do it manually. So that was device control on the individual ones. And you can also read the current interrupt status, obviously. But how many... in this case, it's a kind of side-affecting read. So you're reading the interrupt status, and by reading the interrupt status, you also reset the current interrupt status without needing to have multiple interactions with your device. Just faster. But what actually comes out of your device is one wire. So this device by itself has no means to trigger different sorts of interrupts or interrupts on different priority levels or anything like that. Prioritizing this interrupt or giving this interrupt some meaning has to be happening somewhere else. Now you have to make a decision, where do you solder this wire to? Do you solder this to your bus? Do you solder this directly to your CPU? Do you solder this to an interrupt controller? But whatever you do, you already lost the differentiation possibilities of what happened inside this device. Because all of the interrupts actually already are funneled through a single wire. So whenever this wire is triggered, either you know that you only activated exactly one interrupt anyway, it must be that. But if you have interrupted more than one, what do you need to do? Go back, read the interrupt status register, see what the cause was, which actually triggered this interrupt was. So then there is interrupt controller. Interrupt controllers used to be actual different physical devices. It's becoming a bit exotic that you can actually buy a single chip which is an interrupt controller by itself. Interrupt controllers today are mostly an integral part of your microcontroller design already. So it's all hardwired. And where these wires from your devices go into the interrupt controller, you don't have much choice in that. It's already pre-wired. But you can program the interrupt controller itself, meaning what levels of priorities do you want, how do you want to spread this. So you have basically a matrix operation, you have a few hundred inputs, and you have a few dozen outputs. How do you map and prioritize this whole thing? This is the job of the interrupt controller. Collect, identify, encode, order, and then actually trigger the actual CPU. They can trigger the actual CPU in a number of different ways. You remember what an interrupt vector table was? Ever used that? Ever heard of that? What could that be? Interrupt vector table? Any idea? Yeah, that's one way of describing it, but how do you know which entry you're actually using there in this interrupt vector? Yes, so you have, say, 16 different interrupts which can be coming in, and then you have simply a table of 16 addresses, and those addresses are, this table of your addresses is the so-called interrupt vector. So sometimes you do have some differentiation possibilities. Not all CPUs are triggered by a single interrupt line. Sometimes you have multiple interrupt lines. They can go to multiple addresses. Can you change the entry in the interrupt vector table dynamically at runtime? Can you? Should you?
Not necessarily should you, but at least on some hardware you can.
Yep. So technically, you most of the time can. Sometimes you can also clamp it down, that you say that I write it once and then I switch off this whole area so that I'm no longer accidentally writing on that. And most programming languages, most hard real-time programming languages also make it exceedingly difficult to do that, because that's quite a common source of messing up your system. You replace the interrupt vector someplace, that's usually not a great idea. So how can this appear in practice? I said a universal interrupt controller is quite rare these days. I don't think you will find lots of them. You have dedicated interrupt controllers for similar devices. Think about RAID arrays, classical. So you have a single controller for a whole RAID array, and this also includes an interrupt controller for all the different drives to manage and handle that. Okay, so much for the hardware. What happens on the runtime environment on the operating system level? Let's split that up straight away. Interrupt service routines, communicating interrupts to actual processes, and or directly transforming interrupts into signals. All very different techniques. You have to be clearly identifying what is happening there. Interrupt service routines. An interrupt service routine is completely orthogonal and has no awareness whatsoever about your processes and your tasks in your system. How can that happen? Is the interrupt service routine part of a process? Isn't an interrupt service routine living inside a process? Where do you declare an interrupt service routine? And how can it be that your interrupt service routine has no visibility of processes or tasks?
Processes are just almost an abstraction managed by the operating system anyway, whereas the interrupt service routine is just this bit of code here and there that's executed right now.
You need interrupt service routine to make everything else go, including your processes, your schedulers, all of these kind of things. But the interrupt service routine is something which is defined on the hardware, on the machine level. The CPU has a clear understanding of what interrupt service routine is. It while the CPU, as you say, absolutely no concept of tasks or processes. Please be very clear about this. The moment you talk about what happens on the actual CPU, the concept of the process is all in your head. It's not recognizable, it's not visible on the actual code. So, interrupt service routines cannot operate on the level of threads or tasks, or processes, or whatever you want to call it. What does this imply? If you write your interrupt service routine, we'll see in a second how you write interrupt service routines, but starting from the very principle, from the general point of interrupt service routine, what is not an advisable thing to do from within the interrupt service routine? Wait, stop, because what would that trigger? If you block or wait or stop, what would that trigger?
Wouldn't it more prevent other things from happening?
Now it's even more confusing.
There's no scheduling button, so if you stop.
Yeah, that's another way of explaining it. If you stop, you can of course just stop, but this is not what you want. A process which yields, a process which surrenders the CPU to other processes, has an actual classic pattern, a call pattern to do so. You can inform the scheduler by, for example, putting up some flags or some calls to the scheduler, informing the process control block that I want to sleep, please do something else. So you communicate with something else. Now, your interrupt service routine has not the faintest idea where the scheduler is, or whether it's going to be alive, or whether there is a scheduler in the first place. Where could you possibly wait to? So yes, you can stop, but you cannot suspend yourself so that another process can run.
Interrupt service routines interruptible.
Interrupted.
Other service routines interruptible.
Are service routines interrupted? Are service routines interrupted?
Yes,
And yes, no, maybe, depends. I don't know.
option to temporarily turn off interruptions, which the CPU uses inside of interrupt service routine.
Yeah. Okay, let's put the most brutal case up. I have an interrupt line connected to my CPU, and the device on the outside was a lot faster than I can do. So what happens if the device on the outside is just going absolutely nuts on the interrupt line? Will you just interrupt the service routine, which has been activated on the first press, a few million times afterwards, and again and again and again? Is that a good idea? Is that the default? Can this be the default? Would there be any CPU on the planet where this is the default behavior?
I thought usually you have to disable interrupts manually by an interruption.
No, the other way around.
You got to read it.
For that very reason.
Is that what they call interrupt stalls?
I don't know. That's very If you have interrupts, if you go into an interrupt service routine, what every CPU that I'm aware of will always automatically do is will lift the interrupt priority to the interrupt priority which is currently handled. Which means that the same priority cannot interrupt this interrupt service routine straight away again. Now what you can do manually is you can allow to be interrupted by your own interrupt again by software. Saying, okay, hardware raise the interrupt priority to that specific level, which means that the guy going nuts on the outside will not come through. But I may decide that I want that, so you lower the service priority, the interrupt priority level again, and the interrupt goes through, and it's blocked automatically again until the point where you really allow that. So this is in your control how you want to do that. And yes, you can, and usually interrupt service routines are re-entrant. So it's not a software problem, it's a logical problem. You can call interrupt service routine and even the same interrupt service routine by the same interrupt many times over. You have to be careful if you're not keeping the frequency of this under control. What happens? Stack over. Hang on, should we do the stack one? Why is stack over?
When an interrupt is called, it pushes the level set up in the stack so that it can recover the state.
Okay. As we will see in a second. Yeah.
I think the interrupt service routine is programmable.
Interrupt service routines are programmable.
Yeah, so we will program the interrupt service routine. We can program.
Well, who else will program?
And then what I mean is, and we just can we program with all the concepts in our heads, like with schedule and stuff. We can just program the whole thing how to call the schedule and
Yes.
make it out the process, and then we can just.
How to call a scheduler? Yeah, we'll come to that. It's a bit more complicated in that case.
Yeah, we can just program that.
I don't think that would be a good idea.
Yeah.
The important part is that we have a crystal clear understanding what happens on the hardware, so that we can program the software accordingly without danger of doing anything bad in the process. If you use interrupt service routines on your desktop operating environment, you're lost. On your desktop environment, there's no chance how you can do that. End of story. If you program in a bare-bone runtime environment, as you do on your silent nodes, or if you run a real-time operating system, the story is different. A real-time operating system has, of course, a very clean and clear understanding of interrupt service routines, and you register interrupt service routines in a real-time operating system, similar like you would register a task. Instead of a piece of code, which you don't call a task, but this will become an interrupt service routine. By connecting a specific routine to a specific interrupt vector, and yes, this is a little clunky, and hopefully this can be done a little easier if you have actually a programming language which understands the concept of interrupts. Then you don't need to go through those kind of library interfaces. But if you need to go through an operating system interface, then this is usually what it looks like. You connect a specific address to a specific vector, and you enable it, and you can also explicitly read the address in the vector table, which is associated with a specific interrupt level. So what happens if an interrupt is actually triggered? I colored it from the language operating system level in a number of different places. The first initial response, as I said here, executed by CPU without any involvement of any of your programs, is required to save the current CPU essential registers. What are the essential registers which cannot be recovered by software later?
Is that the instruction pointer?
The instruction pointer, the program counter, obviously. Why is the program counter not recoverable by software?
This is a part of jumping to your interrupt routine. You can change it.
Exactly. Your CPU is just needing to use this program counter to actually make your program go to the interrupt service routine. And at this moment, your program counter is overwritten. Before you override your program counter, because the whole point of triggering interrupt, the first and most important point is that the program counter will be overwritten with a random value which you read out of the interrupt vector table, which means the program counter is toast. And you need to have stored the program counter somewhere. The other thing is certain status flags, the current state of the CPU. Usually it interrupts the CPU status itself, the flags, also in almost all CPUs which I'm aware of, are automatically saved because they're very hard to recover. They, for example, represent the interrupt program. And possibly a few others. Now the next level is either introduced by your operating system or your programming language or your runtime environment. The next level is software. This software level usually saves a few more registers. For example, the registers which you want to use in the interrupt service routine. And if you have programming language and a compiler, well, proxy, because your compiler knows which registers will be used. If you do this by hand, you don't. If you use an assembly or R1C or something like that, you don't. And you need to push evenly everything. That will be on the same side. Stack frame information, then you actually have the code running of the interrupt service routine. Careful, conditions apply. As we said, you cannot do things like you would do from processing. Calling operating system calls in the style of desktop operating system interface, not possible. You cannot do this. And then hopefully, the operating system runtime environment puts the reverse into that as well. And then you need a special, or it's commonly a special CPU register, sorry, a special machine instruction to return from the interrupt. Does that need to be a special instruction? Couldn't that just use another job? Exactly, the status of the whole thing is a bit dodgy. Can you restore the status flags of the CPU? Yeah. Good. Yeah. It's not necessarily the case in all CPU architectures that you can actively restore the state, the flags of your CPU. So if you can, and you know where your CPU left the program counter, and you can manage to get the program counter out of this location, off the system, and jump back manually, you could do that. Now, for comfort, most CPUs will actually give you a special instruction. You can just say, return from interrupt in one shape or the other.
So, yeah.
Is there ever a way of bringing a value directly from stored memory into the program counter? So you
well, it's thinkable. Yeah, but it's two stages. So getting it from memory directly in CPU in the program counter register. Everybody is a bit discouraged for obvious reasons. And I think most CPU designers would actually prefer the safety of avoiding that, so rather than the luxury of being able to do that.
So you would need like a special routine to return the interrupt.
But all you need is doing one mistake.
Okay. Let's have a quick look how this actually looks like if this interrupt hits you. Here's your PC, here's your frame counter, here's your
Yeah.
Sorry, just a quick question. What happens if it tries to push up onto the stack, but it can't write to the memory because it doesn't exist for your random memory?
You're out of memory?
Yeah. Okay. No thing just die.
Yeah.
So,
Sad.
there's no way to recover from that.
What do you expect what happens if you say you have your stack pointer where you store all this kind of information, and your stack pointer runs outside of physically via memory. So your pointer, your physical pointer, not talking about virtual addressing, but about the actual physical addresses, and your pointer is actually running outside of the addresses where memory is stored to. What happens then? Somewhere complain, but what's it? What do you expect? What kind of complaint is it?
If it lets you even call that to memory, then it would just be whatever debugging bugs you're using to attach to the memory would just give back some awaits or 0.
it's just reading atmospheric noise.
Well, yeah, could be plugged into something that's really going anywhere.
Yeah, no, it's not actually happening like that. So, one of the ideas would be you're writing into an area where there is no physical memory solder to, so nothing happens. You just write into the environment, you just send it into nothing. That is exactly not what happens.
Would it call it a non-maskable interrupt that just makes sense?
Non-maskable interrupt, not necessarily that bad, but it will cause an interrupt. What's ever see what this interrupt is called?
Is that a signal?
Yes, for Linux fans, this is called a Linux fan. This is called segfault. What's called on a hardware level? Page fault. Page fault. Yeah, page fault is something to do with memory management.
Yeah, but if you can't map a page to non-existent physical memory, have it?
Yeah, yeah.
You would never get to there because I'm trying to go through virtual memory that you know back in physical page.
Ignore virtual memory management for a moment. What you actually do is you go on your CPU bus and you try to access an address where there is nothing wired to. There is no memory, there is no device, there is nothing there. That means your bus interface will not confirm this right. There's nothing to nobody communicate with because your bus system actually have handshake, synchronization in between. You write to something, you get some synchronization signal back from this device where you have been writing to. There's some handshaking, some overlapping happening. This does not occur. You write to an address and nobody talks to you, no device, no memory, no nothing. Your CPU will raise a bus error. Because you try to work on a CPU bus and nobody was playing. It's a bus error. The bus error, most of the time, will freeze up your system because the interrupt handler for bus error is mostly a pretty mean and severe one. And we'll tell you that this is so severe, I don't have any idea what to do about this. You're playing with devices that don't exist. Let's just stop here.
But when you run a program that's like that, the system doesn't crash.
No, it doesn't. It doesn't just crash. It actually raises an interrupt. But what I'm saying is the interrupt handler, which is in most operating systems or most low-level devices connected to that one, is not doing much else than just panicking. It's putting a red LED up someplace and stops. This is, by the way, also the default behavior of the controller. So if you grab into devices which are no longer wired to anything, this is what you will do. You can change them. If you want to have another response to that, you can override this interrupt handler to something else. So, this is what your stack frame looks like. Just out of curiosity, just to remember what static links, dynamic links are on stacks. You know what they're used for.
It's not related to the shared library.
No, they're not related to shared libraries. Nothing to do with dynamic or static libraries. Come on, guys. We need that in a second. What's the difference between a static and a dynamic link on the stack?
The link is unique to the link to your caller, the one calling calls the static link. I remember is linked to the whole environment, like the variable you can access.
Yes. So the dynamic link is what you have in all programming languages. The dynamic link is a link to the previous stack frame. When will we be using that? Anybody? Yes. When will you be using it from a perspective of higher level programming languages? Exception handling. Why is exception handling dependent on that?
Otherwise, who else would you propagate it to?
You need to know where to propagate your exception to. Propagating an exception means you follow the dynamic links on your stack. If you don't have them, no propagation happens. Thus, you cannot move your stack frame or your stack analysis in case something goes bad and your Java program just dumps the whole stack frame at you. You have 50 different calls with it. Have fun with reading all that and analyzing how deep you have to call when it actually happens. So you also don't have that. Static link, does not appear in all programming languages. The static link is the link to the context, to the surrounding scope. And you need that to have access to all your variables and identifiers in your surrounding scope.
And like local variables, like static variables in C.
Yeah, you don't have scope in C. At least not in standard C. UCC C you do, and you do need to have a scope on the stack in UCC C. So this one actually does have scope, but classical C do not have scopes. So things are either local to your function which you have, or they go on the library. There's nothing in between. While in most programming languages other than that, you have scopes, and you need to identify. That goes for everything else. Pascal, Ada, anything you can imagine has scopes. Very few languages do not. Why did they decide that C doesn't need any scopes? Does it understand the concept?
Can you just go directly to the stack and grab the variables you want anyway?
So that all the C programmers all get no scope.
Performance, speed. You just want to keep the stack as small and simple and primitive as possible. So it's one other little trick to save the work of the stack. None of this gives any speed performance today, but it used to do this in the 70s. So it's one of the historical reasons why that happens. So, interrupt strikes. You put your PC and your flags on the stack, and your PC goes somewhere else. Then in your interrupt service routine, you can declare more local variables, push registers, do lots of funny stuff on the stack, handle device interaction of any sort. Afterwards, you remove your local variables again, pop all the registers which you used locally in your handler, and you call your magic return from interrupt routine. Shall we do this in a more concrete environment, say ARM, just to make you happy with your assignment code? What does it look on your ARM processor? On your ARM processor, the interrupt strikes, this happens. How is that different to what you have seen in the generic case before? So again, we have the program counter and the flags which automatically appear and appear on stack. And these scratch registers will also be saved by your interrupt service routine by default. What are the scratch registers?
So you general purpose registers.
General purpose registers? All of them, some of them? Which of them? So the first four, exactly. So the term scratch register is well defined now. Scratch registers means are 0 to R3. And they are explicitly meant to be unreliable and overwritten by, if you call somebody, you cannot rely on the fact that the scratch registers will survive this. As opposed to the normal registers, where you assume that you call a routine, you get a return value from this routine, and my normal registers hopefully have not changed from that. But your scratch registers can. Which means that on ARM, follow any standard parameter passing protocol, you will not store the scratch registers on the stack because you know that my caller does not expect them to be preserved anywhere. We randomly override them, but that means they're not saved. So if you want to use them here, you better make sure they're automatically saved for you. Hence, this is already done by the hardware. And the link register is loaded with a
special value. We will see why this is the case in a second. So then you can, for example, clear the current interrupt flag, adjust your priorities to your liking. Yeah.
It's the same expression which is on the save by number, but just for interrupts.
Second?
So you're saying that they are saved for interrupts.
Yeah.
Okay. But since we're only saved for scratch registers, does that mean all the interrupt handlers are only use those for scratch registers?
No. No. If you want to use more registers, normal registers, then it's exactly the same as a normal function. So if you write a normal function in ARM environments, you do not save spread registers in your normal function, but you do save all other registers which you plan to use. And it's exactly the same for the graph server, which also makes it very friendly for higher level programming languages now, because you already have the guarantee by the hardware that your functions for the interrupt service routine can be exactly the same code as a normal function. And this is also why we use a very special interrupt return in ARM, which you will see in a second. Yeah.
When it comes to like the non-interrupt handling code, is there any way that it can tell that it has been interrupted?
Can you tell that you have been interrupted?
Is there like a bit that's being set somewhere, or?
The interrupt service routine actually sets some flag. By default, you would have no idea that you would be interrupted. As you just continue on.
So the idea is that you have no awareness that you have ever been interrupted. So it should be completely transparent and abstract from the perspective of the code which is being interrupted. But that doesn't stop you from occasionally, if you want that. You want that your interrupt service routine will make itself noticed to the outside. Otherwise, they're living in different universes. You have your normal code, which has no awareness whatsoever that something happened. And you have your interrupt service routine, which never leaves any traces. That means you have your interrupt service routine and the rest of your code not communicating at all. It's nice if you want to have complete independent concurrency, but it's also pretty boring. Usually what you want is your interrupt service routine handles something, then flags to the rest of your system that something happens, hands over data or communicates with some other form. We'll see how this happens.
So this, just like in a normal routine, you then push all the other registers, you declare your local variables. This all looks 100% like a normal function in ARM programming environments. Do whatever this handler wants to do. And you reverse, just like in a normal function, get the local variables of your stack. What do you do to get the local variables of your stack? Stack pointer down. Variables toast. Well, are they?
Imagine you are the big cybersecurity gurus. Do you want to remove the local variables like this? Why would you not want to do that?
Because the value will still get in the stack.
So you open yourself up for any kind of spoofing that you look into the stack of somebody else after this routine has already returned, because the values are still all there. So in more safety critical environments, you actually have to spend a few more CPU cycles, and these few more CPU cycles are used to actually take the eraser out and wipe all your memory cells empty before you declare them. Balance between performance and safety.
This looks a bit
Okay, let's play a complete example. You have an actual password, an actual key, which decodes something in memory at a certain given time. But the registers you actually need to store in memory because it's too long for your registers. It's a long key. Now, at some point, it will be appearing in memory, simply because you don't have enough register space. That's the choice. You're right. If you have a DMA controller, if you have the system to scan your whole memory at all times at super high frequency, you can be unlucky. But there is still a world of a difference between I store my key for 3 machine instructions in memory, do my XOR, do my calculation, and write the key. Chances that you actually scan the memory at that time and get the full key close to zero. As opposed to you store it on a stack and you return from your routine, and it can take 100,000 machine instructions before you come back to that. That's a major difference. And this is why you usually store it only for an extremely short amount of time. The minimum amount of time you need to do your calculations, then you might do.
Is there a time that you can get the full key? Is it possible to get like bits of the key? Do it multiple times?
Is that mainly in the case of like things where people are trying to, or you're trying to prevent someone from reverse engineering the product that you have, basically?
Yeah, can you prevent reverse engineering?
You can make it difficult.
You can put the product in the black box and just have one button on the side of the product.
Whatever they recommend.
You just make it so the box can go. You can remotely connect to it on the internet and like watch it with the camera. So you make sure
So in this case, is the bad guy a DMA controller, or is it someone who has access to it?
Well,
So the person basically has the device who is using it is the hacker themselves, or?
Your answer is actually not that outlandish, because this is mostly what happens. Not with a security camera, not that, but that you make a black box of it. And you have in your controllers actually switches to read your system. They're actually physical fuses which you can burn in your controllers. And those physical fuses will make it impossible to read out memory. So you burn your program count, your program into your controller, and you burn a fuse. And you cannot get this information out of this memory ever again. The external connection is gone. It's not appearing in the memory once anymore. And all of the devices which you have in an industrial environment are actually programmed like that. Otherwise, reverse engineering would be too easy. Just go to your microcontroller and you go on the CPU bus of that one, trying to get into the memory, and just read out the program code of these guys. Because they're locking this away. And you cannot sell microcontrollers these days anymore, which do not offer these kind of possibilities, because your industrial partner will do something. Like open source.
If you were to, like, for example, reduce the clock speed on the code, like you said with the DMA, it's only there to give it 3 clock cycles. If you were to just massively slow down the clock speed of the CPU, like if you were to, assuming that the microcontroller that you're running, you're providing some kind of external clock to.
Okay. That's an interesting aspect. We try to underclock your CPU that you can actually watch it with your eyes. You should see this thing looks slowly progressing. Not happening, because all of the controllers have also, most of the controllers have also minimum frequencies. They don't work below a certain frequency.
Are they usually massively below the, like, are they only just like a little bit below what you'd usually run it at, or is it?
Yeah, it's pretty quite tight window. I mean, there are exceptions. There are actually controllers which you can basically clock by hand if you want. But this is pretty rare.
Why do you need a minimum frequency? Like public security?
For electrical reasons. Because if you don't have a minimum frequency, then the way you need to actually design your flip-flops so some parts of your CPU work as a dynamic memory element, and dynamic memory elements only work if you drop them fast enough. If you drop them too slow, they're just fading out the information and you lose it. So if you want to have a manually dropped system, you better have actually everything fully flip-flopped through the whole system, that it's all stayed stable, completely the clock cycle. This is not the case in practical CPUs. You have lots of parts in your CPUs which do need minimum frequency to stay alive. Yeah, and then we have the magic branch with a link register. And branch with a link register, do you remember what this usually does on ARM?
Well, it just branches whatever's in the link register.
Exactly. It just jumps to wherever the link register is. So you explain the link register with a program counter. Hang on.
Yeah, you write the link register to the program.
Yes. Do you want that?
This is special.
Exactly. So this is actually not true. This only is done so that from your compiler perspective, you can just generate a code which looks like a normal function. A normal function ends with bxlr. Exchange link register and program counter. And as we store a special value in the link register, your CPU notices that. You try to exchange the program counter with a special value. And this special value tells the CPU what? You're returning from an interrupt, and possibly a bit more. You're returning from which interrupt. It can also contain more information on that one. But the main underlying thing is it actually tells it return from an interrupt, which means that please take this information from the stack, not from the link register. Link register is just code for the stuff that's going to be on the stack, not the link register.
So, what if you try to BX to that address when you're not in the interrupt?
Then you randomly read stuff from the stack. Cool. Do you remember how to use that to do an actual context switch between multiple processes? Could you still program that? Who has done this in 2300? 2. Okay. For the rest, this is a bit of a more scary operation. You could somewhat do it?
Yeah.
Yeah. Okay. This is a good part of what an operating system makes. If you have a context switch, you're halfway to having another operating system in your hand. That works as follows. Obviously, we need to actually do that. We now don't talk about our one main program. We talk about a number of different main programs, and we call these processes. Now, in addition to the actual program, the sequence of operations, we have a process control block. These process control blocks tell you what kind of memory can you use for this process, what I always currently open for that one, what I always allowed for this one, and where's my stack? Very importantly, where is my stack? So if you do an interrupt now, this is all the same thing. Still all the same thing. Ha! Now we do something clever. Yeah? No. No. It's a random piece of memory. And how this is defined is basically your choice of operating system design. Because if you have a multitasking environment, or if you have a runtime environment which has tasking associated with that one, your runtime environment which you have on your controller board does have tasking. Does that? So the ADA runtime environment needs to be able to do exactly that. So the process control blocks, or the information about your ADA tasks, have to be stored somewhere. Where they're stored is completely your design decision. You can have one big array someplace where you store all that. You can have that distributed someplace. This is your design decision. So we store the current stack pointer to the currently running PCB, so currently to PCB1. Then we randomly run our scheduler code. What's the purpose of running the scheduler code? Yep, to figure out who is next. That's the only thing. That can be very, very simple. And in a real-time operating system, you want to have this scheduler code here not only very simple, but also very predictable. So this cannot be a complex heuristic lookup operation. This has to be 100% predictable what is happening there. And the purpose of this scheduler code is finding out who comes next. Namely, found out, of course, we want to load this from PCB2. And we're now loading the stack pointer from the other PCB. Yeah?
Do you need virtual memory at this point? No. So where do you do the stats?
And just define, if you want to do it by hand, no, it's not. Virtual memory, of course, helps. The point is that a lot of the smaller systems, the smaller controllers, do not actually have a virtual memory controller. For those systems, the virtual memory controller is pure conf. It's not actually managing large amount of memory when you solve, because if you have just a single megabyte of memory for your whole system, virtual memory controller is really overkill.
So no, you technically do not need virtual memory to implement that. You can do this manually.
So you just have to be careful with your process to not try to steal the stack.
Yes. Yes, of course. Well, there's different levels of virtual memory controller. You can still have memory protection. Yeah? So this is independent. A full virtual memory controller can actually translate virtual addresses into physical addresses. But you can still have somewhere in between, which gives you the memory protection features which you wanted. You can, for example, store in your process control block which memory areas are currently readable. And when you change over to another process control block, you change that so that the processes cannot physically interfere with each other, or if they do, you get an interrupt triggered. This is still all in plain physical memory without virtualization on top, but you still have memory protection on top of it. And it's of course highly advisable if you want to program a multiprocessing environment that you have some form of memory protection in place. Otherwise, it's just too easy to hack it. Then you remove local variables from the other stack. What local variables are those? How did they ever get there? Yeah. You assume that this process was swapped out at some point as well, or suspended, or blocked, and this is where it gained its local variables there. And you pop the registers on the other side, and you return again from this routine, and you have your context switch programmed.
So the stuff the interrupt push on it, is that still there? Or no?
What is still there?
The interrupt, are we on
The context switch variables, or what do you mean?
No, because the stack code there was interrupted, right?
Yes.
By interrupt handler, and the interrupt handler is a hard to push stuff on the stack.
Yes, it's still there.
And we do know that it's still there.
Still there.
So when the other stack resumes, you have to do a return.
Yes.
And the two keys will go.
As we have done here. So we have the stack looking exactly like the stack here.
Oh, you just swap the two stacks.
Yes, now you get it.
Yeah.
You just swap the two stacks, and then you return from the information which is on the other stack, just like it would have been interrupted a second ago. So cleverly, you now actually combine being interrupted in some control flow, and you return into another control flow. And that gives you a context switch. You now use an interrupt system to change from one process to another.
Yeah, that's part of the creating context. Because I get this.
Doesn't create any context? No, it does. Because now you're actually running.
No, like if you want to run a completely new program to start it up, you're going to have to put you actually know what the software processor puts on it is? Like the drivers and stuff. Like it can do that.
Yeah, you have to feel that. Well, I mean, okay, the startup operation depends very much on the hardware application, how you do that. And you need to possibly make a flag here, take a note here that this process has not been previously interrupted, and I want to change to that, so I do now execute the default piece of code. I don't either emulate the interrupt stack frame, or I need to just execute the code to switch to the process. Here I just showed the example. What happens if I context switch between two processes on a regular basis, and this is what so the initialization is the story. So now you can program this in machine code, in assembly. Yeah, you can. Yeah, sure. And you already have implemented half of an operating system. There's not that much, because now you have tasking. You can change from one process to another one. Cool. What else do you need to write your operating system? What's the minimum definition of an operating system?
You get start programs.
Yeah, you need to initialize this in a clever way. You get this off the ground at some point.
Some virtual memory.
Do all operating systems have the virtual memory construct?
Probably need some kind of I/O. Some way through.
Is I/O necessarily part of an operating system? Okay, what's the bare minimum? What do you expect from the bare minimum before you call something an operating system?
Run programs.
Decent GUI.
You need to be able to run a variable video. That's bare minimum. Technically, what do you require from an operating system that you can actually do bare minimum before you call something an operating system?
Hardware abstraction.
Hardware abstraction. Yeah, so it's giving me a lot of information on kind of features you actually want. Because it's a cop-out. You just say an operating system is basically an abstraction layer. Yeah. But my next question is, what is in this abstraction layer? What do you abstract exactly? But isn't that just a hardware library? Is an operating system nothing but a bunch of hardware drivers, device drivers? Yes? But then it's not part of the operating system.
Well, it's a bunch of other drivers and this. And whatever else. Yes.
Would be basically some like vague symbols of security between processes. Or is that not a requirement?
I mean, this is all pretty debatable, what you define as an operating system. Commonly, an operating system does require some form of tasking, some form of process control, some form of, you can have more than one process in your system. Do you agree? Would you expect the operating system to be able to exchange information, synchronize between your processes in one way or the other? No? You would be happy to have.
If you've got access to a variety, you can through that. Just write the file and then another process reads it from. Can technically.
Wouldn't that be extremely slow and fluffy?
Yeah, we don't need to have it. This is a nice feature.
But you need to predefine all those protocols and all the programs before you get them going. There's no point in your OS. You can talk to that program, be like, you want to talk to him, I'll set up some communication line. So yeah, you get it through your files. You want to tell what file to use.
And what's the minimum hardware which you always want to give access to? Memories. So all operating systems have some form of a memory management system. This can be very, very primitive. This can be nothing but the most primitive heap allocator you have never seen. This can be fun. But you need to have some form of, I want to have 20 bytes of memory, please give me them. You want to have a pointer to them. This is a problem for practice. Does not do that. Probably doesn't really call it time.
This is more just a slight trigger regarding to that comment, but IBM Oz Labs, when they received their CPU prototype, they asked for one of their manufacturers. They didn't have Randall's compatible for it at the time, so they managed to run it by bootstrapping it purely from cache with no RAM. So, yay, an operating system without any RAM, all running within cache.
Okay.
That's not memory. Learn abstraction over.
Yeah, I guess.
Usually I just accidentally recruit that, but they're not.
In a sense, cache is nothing but a very fast memory. So some access to memory and some memory, but that is probably required.
What if you could just lots and lots of registers? Like a lot of registers.
Well, if the operating system was never managed, does it?
This has been tried, and in, say, around the late 80s, there was a sudden growth of the size and the number of registers in CPUs. Before that point, CPUs had usually a program counter, an instruction flag, an accumulator, and maybe a super low luxury register for extreme purposes. And that was it. Then suddenly we had CPUs which had 8 registers. Where they all thought you can use them every way you want. Wow. And they had 16 registers and 32 registers. And what are they doing with all of those? And then the concept of register bands has been introduced, namely CPU designs, where you're not calling another function by pushing something on the stack and getting it back on the stack and pushing further on the stack, but you're only moving your current registers a little bit down. So you're overlapping the registers from the previous call to the next call. Right? So you can hand on over parameters, and by shifting that a little bit, now you have more registers available again. So you roll your whole stack up and down by going up and down your register bank. So yes, this has been tried, this has been done. But it limits your recursion game a little bit. Because at some point you're still running out of register space. And funnily enough, if you have ever seen a physical CPU, you would be scared of the size of registers. Registers are physically gigantic. I know this is not sinking in easily, but a lot of CPUs have a lot more space on the die for their registers, even though there are only 32 registers. Then for the whole of the ALU and other components, the whole vector unit is actually simpler than just your registers. So that doesn't really scale. Having an order of magnitude more registers simply physical.
You just have an external bank of registers.
Well, nice easy. Then you just have physical displacement, and the whole point of the register is lost because you are not getting there in the few nanoseconds which are avoidable to actually read out the value from the registers. So if you have CPUs which are configured at a megahertz, yes, you can do that. But 2 gigahertz, not really. And you need to have stuff very close. And if you look at current CPU designs, the memory modules, the memory banks are also going closer and closer to the actual CPU chip for the same reason, because the memories have become very, very fast today. And delays to physical memory are making slow way to making it redundant to go through cache lines anymore, because the access to memory is something so fast that caches are at least not 3 levels of caches are no longer required.
Does it only like only like 100 cycles away kind of thing?
No, it's not. It has been the case for almost 3 decades. memory speed is about 2 orders of magnitude displaced from the register speed. But look at the specs of current memory modules. And if you look at the top specs of current memory modules, we're talking about 3-4 CPU cycles before you get an answer from the memory module. It's over a factor of 100.
Is it like memory machine?
We're more, let's say, hardcore gaming machines. So it's not your often your laptop which has this kind of memory modules, but if you go even more hardcore, then you will have these kind of memory modules which are fast enough that slowly caches will be coming next. Which actually makes our life so much easier. We don't have to go through 3 levels of caches and 5 virtual memory layers to actually get anywhere. You can use memory pretty much full blast. Not quite as a single memory site. So it's still displaced by, it's not competing with the register. But it's also very different from something which is 100 times slower. 100 times slower is what you probably still have in your machines at the moment, most of them. But this will move away.
Speaking of cache, what happens to the cache in the context switch?
You try to keep it, flush it, get out, get rid of it. This is a whole different world. One of the reasons why I want to get rid of caches because it's complicated and confusing, and you can make lots of mistakes in not flashing the caches at the right point and leaving the cache information after the context switch in the wrong state. So yes, context switches and caching are problematic.
Most real-time processors have the ability to turn off the cache.
Yes. One of the reasons why you would like most of the time to switch off caches completely is because of that mess which comes with that. The unpredictability of context switches and the cache behavior which goes with it.
A friend of mine did that on his machine. It took his terminal about 5 minutes to turn. So he's returning the cache.
Okay.
Okay. So, next level. What do we need to do?
So last thing we will do today. What do we need to do to actually leave any trace? How do you communicate with the process? Shared memory? Tricky.
Just have a read-only memory. For other processes, it should be read-only, and only the interrupt routine can run on
Read-only memory?
For other processes.
Okay.
You put it in system memory and then have to do a system call to read it.
It's a similar form.
Yeah. Like some software interrupts to tell the process head or something.
Yeah. Send a signal.
Send a signal? Yeah.
Yeah, I was going to ask you about how the signal handling works.
Yeah, use a signal. What is a signal? You all happily use that term, but it's not. What's a signal?
It signals something to the program. Like, by instruction.
Recursive.
Signal stuff. Signal?
It should be another task, like operating system level task, and try to synchronize with it.
Yeah.
And
Another task. Now you're really confusing me.
Wait, you're setting a new thread for the signal.
Part of the POSIX standard? Yes, it is. So signals are part of the POSIX standard. And a bunch of other operating systems. But what is logically a signal?
It's just something that conveys information to something else.
What does it convey information to?
Well, that's general signal.
No.
There's a program.
What does it actually, in the first instance, convey information to?
Doesn't it send a message to the programmer to the schedule?
Yes. The signal communicates information scheduler. So it's one indirection displaced. It is telling the scheduler that now, if you ever consider to reactivate this process again, then also please tell this process that this signal occurred. So it's not exactly that responsive and that immediate as what you would associate with meteor. It is going through the scheduler. And it's up to the groups of the scheduler when this actually happens. So the signal in a Linux or Unix operating system or BSD Unix operating system sense is something which is going through the scheduler and is the way it's placed from real-time behavior.
So I noticed that Ada was only using the OS signals for when it's doing audible tasks.
We're doing multiple tasks? Yeah, because
so in the audible section, it receives a signal order.
Yes. Yes. But this is only out of desperation because it runs on top of a desktop operating system. It doesn't have other choice.
So what does it do on the hardware?
It uses action terms. The implementation on the barebone system is very different from that. So on your environment, if you use a selected evolve in your environment, there is no signal in that domain at all. It's like a dark environment. Similar to actually defining the service routines, as we will see for another today, the next time. Defining the service routines if you run on a bare hardware environment. What does that do? If you define into an ADA environment, the service routine, what do you think ADA will do? It just puts this address in the vector table, hard, direct. This interrupt is triggered. Your ADA code, which is associated with that one, is immediately executed. Not scheduled, nothing else in between. Now, the routine which you use for that one has to be a protected procedure. And it has to be a protected procedure because it enables a lot of all the useful communication things which you need to be able to do that. It does provide mutual exclusion from the perspective of the other classes. And it enables you to synchronize and access data in that one in a clean way. Come to that control next time. Here's a variety of things you can possibly do from the perspective of an interrupt handler. This is now completely operating system agnostic, depending on the environment that you have. Ring buffers, shared memory, which is organized in a way that you can guarantee that there's always a space free to write on from your interrupt service routine. Condition free. You have to provide the algorithms to guarantee that. Has to be a ring buffer which is large enough, which you can guarantee there's always free space there. There is no collision there. You can imagine if you can actually signal on an interrupt. Signal on a semaphore. Possible, careful, but it's thinkable that you can trigger signal on a semaphore from interrupt service routine. And how your semaphores are defined in the operating system. Can happen. Similar, of course, from monitors, pipes, anything which is guaranteed to not lead to race conditions and not block your interrupt service routine because your interrupt service routine has no way to be blocked. In order to be blocked, as you saw on the slides before, you need to have a process control block that all the information which you need to reactivate that thing later on again is stored somewhere. Interrupt service routine don't have a process control block. Okay? Cool. Yeah. Raising an exception, does that work?
Yeah, it works.
Does that work?
You just jump to the exception handling code once you find it.
Well, how do you find your exception?
By looking at those tasks.
Looking up the stack.
You find one that registers an exception handler.
So what happens if you get an interrupt while your stack is currently being filled up?
Turn off the front end along the
You can just quit the whole program. Not the whole system, just the program.
We'll actually talk about this. We'll actually blend the concepts of interrupts and exceptions and where they overlap. Some programming languages will actually do what you want. They will treat interrupts and exceptions the same thing. But conceptually, they are mostly very different. Okay. Let's talk about this next time. Thanks a lot.